In the early days of diesel locomotives, one word struck fear into the hearts of railroad crews: downgrade. Every climb has a descent. For every mountain pass conquered on the way up, there's an equally treacherous journey down the other side. Heavy freight trains, thousands of tons of steel, cargo, and momentum, face a fundamental challenge that has haunted railroading since the first tracks were laid through mountain territory. Gravity never stops pulling. In the 1920s and 30s, descending a mountain grade was among the most dangerous tasks in railroading. Engineers would begin the descent with their hands steady on the brake valve, knowing that, for the next hour, perhaps two, they would be locked in a battle with physics itself. The weight of the train wanted to accelerate. The curves of the mountain track demanded control, and the only thing standing between a controlled descent and catastrophe was air pressure and friction, two forces that could fail, fade, or simply prove insufficient. The accidents that resulted weren't rare occurrences. They were regular, predictable tragedies. Runaway trains on mountain grades claimed lives, destroyed equipment, and haunted the industry. Crews developed techniques, workarounds, and desperate measures to maintain control. They added water cars for extra weight and braking power. They used drift braking, carefully timing the application and release of brakes to prevent overheating. They prayed. Then came an innovation so elegant, so transformative, that it changed mountain railroading forever. Engineers realized that the same electric motors that pulled trains uphill could be reversed, turned into generators that would slow trains on the descent. This technology had no moving parts that wore out from friction. It didn't fade with heat. It didn't depend on air pressure that could leak or deplete. It was called dynamic braking, and it saved countless lives. This is the story of how electricity tamed the mountains, how physics solved what mechanics couldn't, and how a technology developed in the 1930s continues to protect every heavy freight train that winds its way down from high mountain passes today. To understand the revolution that dynamic braking represented, we need to understand the world that existed before it, a world where descending a mountain grade was one of the most hazardous operations in railroading. The story of train brakes begins with George Westinghouse. In 1872, he patented the automatic air brake, a system that used compressed air to apply braking force to every car in a train simultaneously. Before Westinghouse, trains used hand brakes that had to be manually applied by brakemen running along the tops of moving cars, tightening brake wheels one car at a time. It was dangerous, slow, and hopelessly inadequate for long, heavy trains. The Westinghouse air brake was revolutionary. Compressed air from the locomotive traveled through a continuous pipe running the length of the train. When the engineer reduced air pressure in this pipe, brakes on every car applied automatically. The system was fail-safe. If the train separated, the loss of air pressure would automatically apply the brakes. It made long trains practical and dramatically improved safety. But the air brake had a fundamental limitation that became critical on mountain grades: heat. When a train descends a grade, gravity continuously accelerates the train. To maintain a safe speed, the brakes must continuously convert that kinetic energy into heat through friction. Brake shoes, cast iron, or later composite blocks press against the steel wheels, and the friction generates enormous temperatures. On a long descent, those temperatures can exceed 600 degrees Fahrenheit. At these temperatures, several things happen, all of them bad. The brake shoes themselves begin to break down. The metal expands and warps. Most critically, the friction coefficient decreases. The brakes become less effective precisely when they're needed most. This phenomenon is called brake fade, and on a mountain grade with a heavy train, it could mean the difference between control and disaster. Engineers developed techniques to manage these limitations. One method was drift braking, applying the brakes in intervals to slow the train, then releasing them to let the shoes cool before applying again. This required careful judgment and constant attention. Apply the brakes too long, and they'd overheat and fade. Release them too long, and the train would accelerate beyond control. On particularly severe grades, railroads added water cars to trains, tank cars filled with water, positioned near the rear of the train. The added weight increased the train's momentum, paradoxically making it easier to control by increasing the effectiveness of braking on the locomotive and forward cars. Some railroads used retarders, track-mounted brake systems at specific points on the descent. But these were fixed installations that couldn't adjust to varying train weights or conditions. The human cost of these limitations was measured in accidents. Cajon Pass in California, connecting the high desert to the Los Angeles basin, was notorious. The grade descends more than 2,000 feet in less than 25 miles, with curves and a sustained grade of over 2%. Before reliable dynamic braking, runaways on Cajon were regular occurrences. In some years, multiple trains lost control on the descent. Saluda grade in North Carolina held the distinction of being the steepest standard gauge mainline railroad grade in the United States, 4.7% in places. Trains ascending Saluda required helper locomotives. Trains descending it required extraordinary care. The grade claimed numerous locomotives and cars over the decades of its operation. Donner Pass in the Sierra Nevada presented its own challenges. The grade itself was steep, over 2% in sections, but winter conditions made it treacherous. Snow, ice, and sub-zero temperatures affected brake performance unpredictably. Engineers descending the east slope of Donner in winter faced a descent where even minor misjudgments could have catastrophic consequences. The railroads knew these risks. Crew training emphasized mountain operations. Rules governed maximum train weights on specific grades. Helper locomotives were stationed at the base of grades to assist both climbing and descending trains. But all of these measures worked around the fundamental limitation. Air brakes alone were not sufficient to safely control heavy trains on long, steep descents. The solution, when it came, would not come from improving air brakes. It would come from a completely different source, from the new diesel-electric locomotives that were beginning to replace steam power in the 1930s. The diesel-electric locomotive represented a fundamentally different approach to railroad motive power. Unlike steam locomotives, which used reciprocating pistons to directly drive the wheels, diesel-electrics used an indirect system. A diesel engine turned a generator, producing electricity. That electricity powered traction motors mounted on the axles, and those motors turned the wheels. This arrangement offered numerous advantages. Diesel-electrics could produce consistent power at any speed. They didn't require the massive boiler and water supply of steam locomotives. They could be operated in multiple unit configurations with a single crew controlling several locomotives. But it was a side effect of this electrical system that would prove transformative for mountain operations. Engineers and designers at General Electric and the electromotive division of General Motors realized something elegant about the traction motor design. The same machine that converted electricity into motion could, with relatively simple modifications, convert motion back into electricity. A motor and a generator are, fundamentally, the same device running in opposite directions. The principle is electromagnetic induction. When electricity flows through coils in a magnetic field, it produces motion. This is a motor. When motion turns coils in a magnetic field, it produces electricity. This is a generator. The traction motors that propelled the locomotive could be switched to generate electricity when the wheels were turning, and that generation would create resistance that opposed the motion. The train would slow down. But there was a problem to solve: what to do with the electricity being generated. In a locomotive, there was no practical way to store large amounts of electrical energy. Batteries of sufficient capacity would be impossibly heavy. The solution was elegant in its simplicity. Convert the electrical energy into heat and dissipate it to the atmosphere. This was accomplished using resistor grids, banks of heavy-duty electrical resistors mounted on the roof of the locomotive. When the traction motors were generating electricity, that current was fed through these resistors. The resistors heated up substantially, and large fans mounted on the roof blew air across them, carrying the heat away. This system became known as dynamic braking, or sometimes rheostatic braking. The kinetic energy of the moving train was converted to electrical energy, then immediately converted to heat and exhausted. The train slowed without any friction between brake shoes and wheels. The first practical applications came in the mid-1930s. General Electric and Electromotive Corporation both developed systems for their early diesel-electric designs. The technology was initially viewed with some skepticism. Railroads were conservative institutions, and adding complexity to locomotives always raised concerns about reliability and maintenance. But the early tests, particularly on mountain grades, were compelling. Locomotives equipped with dynamic braking could descend grades that had been treacherous for steam locomotives, maintaining steady speeds without the brake shoe overheating that plagued conventional air brakes. The system didn't eliminate air brakes. Those remained essential for stopping and parking, but it provided a powerful supplementary braking force that could be applied continuously without fade. The Santa Fe Railway was an early adopter, testing dynamic braking on its routes across Raton Pass and, critically, on Cajon Pass. The results on Cajon were particularly striking. Trains that had required extreme caution and sometimes helper locomotives for the descent could now be safely controlled by the engineer using dynamic braking, with air brakes held in reserve for final speed control and stopping. The electromotive FT freight locomotive, introduced in 1939, offered dynamic braking as an option. By the time EMD introduced the F3 model in 1945 and the F7 in 1949, dynamic braking was standard equipment on units sold to railroads with significant mountain operations. The distinctive dynamic brake fans on the roof of these locomotives became a visual identifier. You could tell at a glance whether a locomotive was equipped for mountain service. The technology spread rapidly through the 1940s and 50s. As diesels replaced steam across American railroads, dynamic braking became standard on road freight locomotives. The Union Pacific, with its routes across the Rockies and the Sierra Nevada, specified dynamic braking on its entire diesel fleet. The Southern Pacific, operating over Donner Pass and the Tehachapi Loop, did the same. The Denver and Rio Grande Western, running through the heart of the Rockies, considered it essential equipment. By the 1960s, dynamic braking had evolved from an innovation to an expectation. Locomotive builders offered it as standard or optional equipment, depending on the customer's territory, but any railroad operating in mountainous terrain specified it without question. The system had proven itself not just in performance, but in safety. The accident rate on mountain grades had dropped dramatically with the adoption of dynamic braking. What had begun as a clever application of electromagnetic principles had become one of the most important safety technologies in railroading, and it would continue to evolve. Dynamic braking operates on principles of physics that are elegant in their simplicity. Yet the engineering that makes it practical for railroad operations is sophisticated and precise. At the heart of the system are the traction motors. In a diesel-electric locomotive, these motors are mounted directly on the axles, with each powered axle having its own motor. On a typical 6-axle locomotive like an EMD SD50-2 or a GE-9, there are 6 traction motors, each capable of producing several hundred horsepower. When the locomotive is pulling a train, the sequence of energy conversion is straightforward. The diesel engine turns a main generator. That generator produces electricity on older DC systems. This is direct current. On newer AC systems, it's alternating current. This electricity flows to the traction motors. The motors convert electrical energy into rotational motion, turning the wheels and propelling the locomotive. Dynamic braking reverses this process. When the engineer activates dynamic braking, the electrical system reconfigures. The traction motors are disconnected from the main generator and instead connected to the resistor grids. Now, instead of receiving electricity to produce motion, they're configured to generate electricity from motion. As the train rolls forward, the wheels turn. The wheels turn the axles. The axles turn the traction motors. The traction motors, now acting as generators, produce electricity. This generation creates a magnetic resistance. The same electromagnetic forces that produce motion when the motor is powered now resist motion when the motor is generating. The train slows. The electricity produced by the motors has to go somewhere. This is where the resistor grids come into play. These are banks of heavy-duty electrical resistors, materials with high electrical resistance that convert electrical current into heat. On a typical locomotive, the resistor grids are housed in a large ventilated compartment on the roof, often visible as a raised section or blister on top of the locomotive. When current from the generating traction motors flows through these resistors, they heat up rapidly and intensely. The amount of heat is substantial. A heavy freight train descending a mountain grade might generate several thousand horsepower worth of braking force through dynamic braking, and all of that energy becomes heat in the resistor grids. To prevent the resistors from overheating and failing, large cooling fans are mounted in the roof compartment. These fans, powered by the locomotive's auxiliary systems, force air across the resistor grids at high volume. The hot air is exhausted through vents, typically at the ends of the resistor compartment. On a cold day, you can see the heat shimmer rising from a locomotive using dynamic braking. At night, if you look closely, you might catch a faint orange glow from the resistors themselves. The amount of braking force produced by dynamic braking is controllable. The engineer has a dynamic brake handle in the cab, similar to, but separate from the air brake handle. Moving this handle adjusts the amount of electrical load applied to the traction motors. More load means more resistance, which means more braking force. The system provides precise, graduated control. Modern locomotives include an ammeter that displays the current being generated during dynamic braking, typically measured in amperes. An engineer descending a grade watches this meter carefully. It provides real-time feedback about how much braking force the dynamic brakes are producing. If the amperage drops unexpectedly, it might indicate that the locomotive is approaching the low-speed limit of effective dynamic braking. This brings us to one of the important limitations of dynamic braking. It becomes less effective at low speeds. The braking force produced is proportional to the speed of the wheels. At high speeds, the motors generate substantial current and produce strong braking. As the train slows, the motors generate less current and the braking force decreases. Below about 10 to 15 miles per hour, dynamic braking produces minimal force. This is why dynamic braking doesn't replace air brakes, it supplements them. On a long mountain descent, the typical procedure is to use dynamic braking to control speed on the continuous grade, holding the train at a safe speed. Air brakes are held in reserve, used intermittently to fine-tune speed or to supplement dynamic braking if needed. When the train approaches curves, junctions, or the bottom of the grade where it needs to slow to lower speeds or stop, the engineer transitions from dynamic braking to air braking. The blending of dynamic and air braking requires skill and judgment. Too much reliance on air brakes on a long grade risks brake fade. Too much reliance on dynamic braking without air brake backup means less control if the dynamic system fails or becomes less effective. Experienced engineers develop a feel for their territory, knowing where to apply each system for optimal control. The sound of dynamic braking is distinctive. The traction motors, when generating, produce a deep electrical hum that varies in pitch with speed. The cooling fans create a loud rushing sound. On older locomotives with mechanical fans, this can be a roar. Rail fans who spend time trackside learn to recognize these sounds. When you hear the characteristic fan roar and motor hum from a locomotive on a descending grade, you're hearing dynamic braking at work. Weather affects dynamic braking performance. Cold air is denser and cools the resistors more efficiently, allowing sustained high braking effort. Hot weather reduces cooling efficiency, and in extreme heat, the resistors can reach their thermal limits, forcing the system to reduce braking force or temporarily shut down to prevent damage. This is particularly relevant in desert mountain operations, where summer temperatures can exceed 100 degrees Fahrenheit, while locomotives are generating thousands of kilowatts of heat. Maintenance of dynamic braking systems is critical. The resistor grids must be inspected regularly for damage or deterioration. The cooling fans must be maintained. A failed fan can quickly lead to overheated resistors. The electrical switchgear that configures the motors between powering and generating modes must be kept in proper adjustment. Modern locomotives include monitoring systems that alert the crew if dynamic braking performance degrades. The effectiveness of dynamic braking varies with locomotive design and configuration. DC traction motor systems, used on locomotives built from the 1940s through the 1990s, provide strong dynamic braking but have limits on low-speed effectiveness. AC traction motor systems, introduced in the 1990s and now standard on new locomotives, provide improved dynamic braking that remains effective to lower speeds and operates more efficiently across a wider range of conditions. On heavy freight trains, the dynamic braking from the locomotives alone might not be sufficient. This is where distributed power comes in. Additional locomotives placed in the middle or at the rear of long trains, all controlled by radio from the lead locomotive. These remote locomotives can apply their dynamic braking in coordination with the lead units, distributing the braking force throughout the train. This prevents slack action, the bunching and stretching of couplers that can lead to derailments, and provides much greater total braking capability. The physics is simple. Convert kinetic energy to electrical energy to heat, and dissipate that heat to the atmosphere. but the engineering that makes it reliable, controllable, and safe for trains weighing 10,000 to 20,000 tons descending grades for miles represents decades of refinement and development. It's technology that works in extreme heat and extreme cold, in rain and snow, day after day, train after train. And it's technology that has fundamentally changed what's possible in mountain railroading. The true measure of dynamic braking's impact isn't in the engineering specifications or the physics principles. It's in the mountain passes where railroads operate every day, where the difference between controlled descent and catastrophe is measured in the reliability of braking systems. Let's explore several of the most challenging mountain operations in North American railroading and how dynamic braking transformed each of them. Donner Pass, the Sierra Nevada. Donner Pass, crossing the Sierra Nevada between California and Nevada, is one of the most storied and challenging mountain crossings in American railroading. The original transcontinental railroad crossed here in 1869, and the route has been in continuous operation ever since. The east slope of Donner Pass is the critical section. Trains ascending from the Nevada side face grades of 2.2%, steep enough to require careful power management and sometimes helper locomotives. But it's the descending trains that face the greater challenge. A train descending from the summit near Northern California toward Truckee and beyond must control its speed for more than 20 miles of continuous grade. In the steam era, this descent was treacherous. Heavy freight trains required constant attention to braking, and runaways, while not frequent, were a known risk. The Southern Pacific Railroad, which operated Donner Pass for most of its history, stationed helpers at both ends of the pass and enforced strict tonnage limits. Winter conditions made everything worse. Donner Pass is named for the ill-fated Donner Party, trapped by early snows in 1846. The pass regularly receives 30 to 40 feet of snow annually, and winter operations require extensive snow fighting infrastructure. In these conditions, brake performance becomes even more critical and less predictable. Dynamic braking changed Donner Pass operations fundamentally. Diesel locomotives equipped with dynamic braking could descend the east slope, maintaining steady speeds of 25 to 30 miles per hour, without the brake fade that had haunted steam operations. The system worked as effectively in winter as in summer. The cold air actually improved cooling efficiency for the resistor grids. Today, Union Pacific operates Donner Pass with modern AC traction locomotives featuring sophisticated dynamic braking systems. Heavy unit coal trains and intermodal trains routinely cross the pass, their descent controlled primarily by dynamic braking, with air brakes used for supplemental control. The accident rate on Donner's east slope, once a source of constant concern, has become negligible. Cajon Pass, the desert approach to Los Angeles. If Donner Pass is historic, Cajon Pass is infamous. Located about 60 miles northeast of Los Angeles, Cajon connects the high desert of the Mojave with the Los Angeles Basin. It's the primary railroad gateway for freight traffic entering Southern California from the east. The statistics are daunting. A descent of over 2,000 feet in approximately 25 miles, with sustained grades of 2 to 2.2% and numerous curves. Trains descending Cajon must navigate this route while maintaining control despite enormous weight. Modern freight trains can exceed 15,000 tons. Cajon's history is marked by accidents, many of them runaways. In the steam era and early diesel era, trains that lost braking control on the upper sections of Cajon faced a terrifying reality. There was no safe way to stop. The grade was too long, the curves too tight, and the speed would build until something broke or derailed. The Santa Fe Railway, which operated Cajon for much of its history, was an early and enthusiastic adopter of dynamic braking specifically because of this pass. The first diesel units with dynamic braking tested on Cajon in the late 1930s and early 1940s demonstrated dramatic improvements in control and safety. Despite dynamic braking, Cajon remained challenging enough that tragedy could still occur. In 1989, a Southern Pacific freight train lost control on the pass, accelerating to an estimated 90 miles per hour before derailing in a residential area of San Bernardino. 4 people died, and dozens of houses were destroyed. The investigation revealed that the dynamic braking on the locomotives had failed, and the crew had not applied sufficient air braking to compensate. This accident led to significant changes in procedures and technology. Railroads implemented more stringent pre-departure brake testing, installed additional trackside safety systems, and modified training protocols. Modern operations on Keijon feature mandatory use of distributed power, remote locomotives throughout the train, providing additional dynamic braking capacity, and strict enforcement of operating procedures. Today, BNSF Railway operates Keijon Pass with some of the heaviest freight trains in North America. These trains descend the pass with dynamic braking from multiple locomotives distributed throughout their length, coordinated by computerized control systems. The transformation from the accident-prone route of the mid-20th century to the reliably safe operation of today is directly attributable to dynamic braking technology and the operational procedures built around it. Tehachapi Loop, engineering and braking combined. The Tehachapi Loop, also in California, represents a different approach to mountain railroading. Rather than fighting a steep grade directly, the railroad loops back on itself, passing over its own track inside the loop to gain elevation more gradually. It's one of the most photographed railroad locations in North America, but the engineering elegance of the loop doesn't eliminate the braking challenge. Trains descending from the Tehachapi summit toward Bakersfield must control their speed through continuous curves and grades of 2%. The loop itself adds complexity. Long trains actually overlap themselves inside the loop, with the head of the train above the rear of the same train. Dynamic braking is essential for Tehachapi operations. The continuous nature of the descent means air brakes alone would overheat long before reaching the bottom. Modern operations use distributed power extensively. Long trains might have 4 or 5 locomotive consists spread through their length, all applying dynamic braking and coordination. The distinctive sound of heavy trains descending Tehachapi, the combined roar of dynamic brake fans from multiple locomotives echoing off the mountainsides, has become iconic to rail fans who visit the location. Moffett Tunnel and the Continental Divide. The Moffett Tunnel, cutting through the Continental Divide in Colorado, represents high-altitude mountain railroading at its most challenging. The tunnel itself is 6.2 miles long, one of the longest railroad tunnels in North America. The approaches on both sides involve sustained grades. For trains descending the east slope from the tunnel toward Denver, dynamic braking is critical, not just for control, but for managing the transition from the thin air at 9,000 feet elevation to the thicker air below. Diesel engines perform differently at different altitudes, and the cooling requirements for dynamic braking resistors change with air density. The Denver and Rio Grande Western, which operated this route before merging with Southern Pacific and later Union Pacific, specified heavy dynamic braking capacity on all locomotives assigned to the Moffett Tunnel route. Today's operations maintain that tradition, with modern AC traction locomotives providing powerful and reliable dynamic braking for the challenging descent. Tennessee Pass, abandoned but not forgotten. Tennessee Pass in Colorado, at 10,140 feet elevation, was once one of the highest railroad crossings in North America. The Denver and Rio Grande Western operated this route for decades, moving freight between Denver and Salt Lake City through the heart of the Rocky Mountains. The grades on Tennessee Pass were severe, 3% in places, and the elevation meant reduced power from diesel engines. Dynamic braking was absolutely essential for controlling descents on both sides of the pass. Trains sometimes used helper locomotives positioned at the rear, applying dynamic braking during the descent to prevent slack action and provide distributed braking force. Union Pacific closed Tennessee Pass through traffic in 1997, choosing to route trains through Wyoming instead. But the infrastructure remains, and the pass stands as a testament to an era when railroads operated in terrain so challenging that every technological advantage, including dynamic braking, was essential just to maintain safe operations. Narrow-gauge mountain railroading. For a contrast, consider the narrow-gauge mountain railroads that still operate in Colorado, the Durango and Silverton Narrow-Gauge Railroad, and the Cumbres and Toltec Scenic Railroad. These lines use restored steam locomotives operating over grades and curves, as challenging as any in North American railroading. Without dynamic braking, crews on these trains rely on the traditional methods: careful speed management, drift braking with the air brakes, and sometimes water-filled tender tanks for additional weight and braking force. The skill required to safely descend grades like Cumbres Pass, with grades exceeding 4%, is extraordinary. Riding in the cab of a steam locomotive descending such a grade provides visceral appreciation for what dynamic braking solved. The engineer's constant attention to speed, the periodic application and release of air brakes, the careful management of steam to avoid accelerating the train, all of this represents the old reality that dynamic braking made obsolete for modern freight operations. These historic operations preserved not just steam locomotive technology, but the operational practices that were standard before dynamic braking. They're living museums of railroad practice, and they demonstrate by contrast just how transformative dynamic braking has been for modern mountain railroading. Across all these mountain passes, the story is the same. Dynamic braking transformed operations from dangerous and uncertain to reliable and safe. It didn't eliminate risk. Railroading remains a serious business requiring skilled operators and constant vigilance. But it removed the constant threat of brake fade and runaway that had haunted mountain operations since the first railroads were built through challenging terrain. Dynamic braking, as originally developed in the 1930s and refined through the diesel era, solved a critical problem. It provided fade-free braking for mountain descents. But it had one significant inefficiency. All the energy of the descending train was converted to heat and dissipated to the atmosphere. Thousands of horsepower worth of energy simply thrown away. For decades, this was accepted as the necessary cost of the system. The technology to do anything else simply didn't exist in practical form. But as electrical technology advanced and environmental consciousness grew, engineers began asking, could that energy be captured and used instead of wasted? The answer is regenerative braking, a system that returns the electrical energy generated during braking back to the power source instead of dissipating it as heat. The concept is simple in principle but requires sophisticated technology to implement in practice. Regenerative braking requires a place for the generated electricity to go. In electric locomotives drawing power from overhead catenary or third rail, this is straightforward. The electricity is fed back into the catenary system, essentially running the locomotive's electrical meter backwards. The energy then becomes available to other trains on the same electrical system, or flows back to the utility grid. European and Asian railroads with extensive electrification have used regenerative braking for decades. Swiss Federal Railways, operating in one of the most mountainous regions in Europe, has refined regenerative braking to an art form. Heavy freight trains descending the slopes of the Alps generate substantial electrical power that flows back to the catenary system. Other trains climbing in the opposite direction can use that power immediately. The overall energy consumption of the railroad network is significantly reduced. The numbers are substantial. A heavy freight train descending a mountain grade can generate megawatts of power through regenerative braking. Over the course of a year, across a busy mountain corridor, the energy recovered amounts to millions of kilowatt hours, enough to power thousands of homes. China's rail system, which includes extensive high-speed passenger networks and heavy-haul freight operations in mountainous regions, relies heavily on regenerative braking. The country's investment in electrified rail, now the most extensive in the world, was partly justified by the energy efficiency that regenerative braking provides. Trains descending mountain grades in provinces like Shanxi and Shaanxi, carrying coal from inland mines to coastal ports, return enormous amounts of energy to the grid. For diesel-electric locomotives, which remain the standard for freight operations in North America, implementing regenerative braking is more challenging. There's no catenary to feed power back into, and the diesel engine and generator aren't designed to receive electrical power from the traction motors. Some solutions have been developed. Hybrid locomotives, equipped with large battery banks, can store energy from dynamic braking for later use. When the locomotive accelerates, power can be drawn from the batteries rather than solely from the diesel engine, reducing fuel consumption. General Electric and others have developed such locomotives for switching and short-haul operations, where the frequent acceleration and braking cycles make energy recovery particularly valuable. For road freight locomotives, the development that has most improved dynamic braking effectiveness is AC traction technology. Beginning in the 1990s, builders introduced locomotives using alternating current traction motors rather than the direct current motors used since the dawn of diesel-electric technology. AC motors provide several advantages for dynamic braking. They generate effective braking force down to much lower speeds than DC motors, remaining effective to 5 miles per hour or less instead of becoming weak below 10 to 15 miles per hour. They operate more efficiently across wider temperature ranges. And the inverter technology that controls AC motors allows more precise, computer-managed integration of dynamic braking with air braking. Modern AC traction locomotives include sophisticated microprocessor control systems that automatically blend dynamic and air braking to maintain target speeds on grades. The engineer sets a desired speed, and the computer manages both braking systems to maintain that speed, adjusting automatically for grade changes, train weight, and braking system performance. These systems also coordinate dynamic braking across distributed power consists. In a modern heavy freight train, there might be 3 or 4 groups of locomotives distributed throughout the train's length, at the head, in the middle, and at the rear. All of these locomotives can apply dynamic braking, but they must do so in coordination to avoid inducing slack action that could cause derailments or coupler failures. Radio-based distributed power systems allow the lead locomotive's computer to command remote locomotives in real time. When the engineer applies dynamic braking, all locomotives throughout the train apply their dynamic brakes proportionally. The system continuously monitors individual locomotive performance and adjusts to compensate for variations. If one remote locomotive's dynamic braking becomes less effective, perhaps due to overheating resistors, the system can increase braking effort on other locomotives to maintain overall train control. The evolution toward computer control has also improved safety. Modern locomotives include event recorders, essentially black boxes like those on aircraft, that record all engineer actions and all automatic system responses. If an incident occurs, investigators can review exactly what braking forces were applied, how systems responded, and whether procedures were followed. Some railroads have implemented additional automation layers. Positive train control systems, now mandatory on most U.S. mainlines, can automatically apply braking if a train exceeds speed limits or approaches hazards. These systems integrate with dynamic braking controls, allowing automated intervention if needed. Looking forward, the next generation of locomotive technology might finally bring true regenerative braking to North American freight railroads. Concepts under development include catenary electrification of high-traffic corridors, battery electric locomotives with sufficient capacity for road service, and hybrid systems that combine diesel engines with substantial battery storage. The fundamental principle established in the 1930s, using traction motors as generators to create braking force, remains unchanged. But the sophistication of the control systems, the efficiency of the electrical components, and the integration with other train systems have advanced enormously. What began as a simple solution to brake fade has evolved into a sophisticated energy management system that improves both safety and efficiency. Dynamic braking, as originally conceived, saved lives by preventing runaways. Modern regenerative and computer-controlled systems continue that safety mission, while adding environmental benefits through energy recovery and reduce fuel consumption. The technology that tamed the mountains is now helping to make railroads more sustainable for the future. There are technologies in railroading that attract attention and admiration. The massive diesel engines producing thousands of horsepower, the sophisticated signaling systems coordinating train movements, the engineering marvels of tunnels and bridges spanning impossible terrain. Dynamic braking gets less attention. It's not visible from trackside unless you know what to look for. The distinctive fans on locomotive roofs might be noticed, but their purpose isn't obvious. The deep hum of traction motors generating electricity during a descent is audible only to those who know to listen for it. Yet dynamic braking represents one of the most significant safety advances in railroad history. Before its introduction, mountain railroading was inherently dangerous. Runaways were a constant threat. Crews descending long grades knew they were engaged in a battle with physics where the margin for error was thin and the consequences of failure were catastrophic. Dynamic braking didn't make mountains smaller. It didn't make grades less steep or curves less sharp. What it did was give engineers a tool that worked reliably, that didn't fade with heat, that could be applied continuously for hours without degradation. It transformed descents from desperate exercises in brake management to controlled, predictable operations. The statistics tell the story. In the decades before dynamic braking became standard, mountain railroads experienced regular runaway incidents. Crews were killed, equipment was destroyed. Communities near the base of steep grades lived with the knowledge that a runaway train might come through at any time. After dynamic braking was widely adopted in the 1950s and 60s, the frequency of runaways dropped precipitously. Routes that had been notorious for accidents became routine operations. This wasn't just about preventing dramatic catastrophes. Dynamic braking also reduced the wear and tear on equipment that occurred from constant heavy use of air brakes. Brake shoes lasted longer. Wheels stayed rounder, without the flat spots that developed from locked wheels sliding. Maintenance costs decreased even as safety improved. The human element cannot be overstated. Railroad engineers who worked both before and after dynamic braking became standard describe the difference in terms that go beyond technical specifications. They talk about stress, about the constant tension of a long descent with only air brakes, about the relief of having dynamic braking available as a primary control method. The job became safer not just in accident statistics but in daily practice. Consider what it means to descend a grade like Cajon Pass or Donner Pass with a 10,000-ton freight train. The descent might take an hour or more. Every minute of that time, gravity is accelerating the train. Every curve demands controlled speed. Every junction, every grade change, every potential hazard requires attention. Before dynamic braking, engineers managed this with air brakes that heated up, faded, and required constant monitoring. After dynamic braking, they had a tool that worked as well in the last mile as in the first. The technology spread beyond mountain railroading. Dynamic braking proved valuable in other contexts: long descending grades in relatively flat territory, operations in regions with frequent stops, anywhere that thermal management of conventional brakes was a concern. But it was in the mountains that its value was most obvious and its impact most profound. There's a particular kind of achievement in technologies that become invisible through their success. Dynamic braking is so reliable, so routine, so thoroughly integrated into normal railroad operations that it's easy to forget it's there. Modern engineers grow up with it. It's not a special feature, it's just how locomotives work. The dynamic brake handle in the cab is as fundamental as the throttle and the air brake valve. But spend time with historians of railroading, or with engineers who remember the transition from steam to diesel, or with safety specialists who study accident records, and the story becomes clear. Dynamic braking stands among the most important safety innovations in railroad history, comparable to the air brake itself, or to modern signaling systems. Tonight, somewhere in North America, a freight train is descending a mountain grade. The locomotives at the head of the train and the distributed power units in the middle and rear have their traction motors configured for generating. Electricity flows through resistor grids on the locomotive roofs. Cooling fans roar, pushing heated air into the night. The ammeter in the cab shows steady current. The train maintains exactly the speed the engineer has commanded, steady and controlled, mile after mile. The engineer watches the track ahead, monitors the instruments, and makes small adjustments as needed. It's routine. It's safe. It's possible because of a technology developed in the 1930s that turned the problem of controlling heavy trains on mountain grades from a dangerous gamble into a predictable science. The fans hum. The resistors glow faint orange in their ventilated housing. The train descends under control, as it has thousands of times before on this route. And somewhere in that routine operation, in that unremarkable safety, lies one of the quiet triumphs of railroad engineering. Dynamic braking changed mountain railroading. It saved lives, countless lives, including lives of people who never knew they were at risk, because the technology prevented accidents before they could happen. It made possible operations that would have been too dangerous to attempt with air brakes alone. And it continues, every day, every mountain descent, every heavy freight train, to do the same work it has done for more than 80 years, converting motion into electricity into heat, and danger into safety. That's the story of how dynamic braking changed mountain railroading, not with drama, not with fanfare, but with physics, engineering, and the quiet competence of technology that simply works. The mountains remain as steep as they ever were, but the trains that cross them are no longer at the mercy of gravity and fading brakes. They're controlled by electromagnetic forces, by heat dissipation, by the elegant principle that the same motors that pull a train uphill can slow it down on the descent. It's a technology that deserves to be remembered and understood, even if it does its work quietly, out of sight, in the electrical systems and cooling fans atop locomotives crossing mountain passes in the dark. Because sometimes the most important innovations are the ones that prevent the disasters that never happen, that save the lives that were never lost, that transform danger into routine safety through nothing more than applied science and careful engineering. That's the legacy of dynamic braking, and every train that safely descends a mountain grade is a testament to its success.